SVMs can also be used for nonlinear regression problems, and we will see how that setup can be done and how we can proceed to the solution to that problem. But before we discuss the setup of this regression problem, we need to understand something regarding epsilon insensitive loss functions. So, let us see how this can be done. So, our goal is to come up with a robust estimator for a regression problem insensitive to small changes in the model. I mean, this is a non-parametric form, so I did not specifically bring in the parameters here. Now, what are the general problems that we see with other forms of estimators such as a least squares estimate? The least squares estimator is sensitive to the presence of outliers. This is very important. It is sensitive to the presence of outliers and performs poorly over distributions that have long tails. So, sometimes it is better to have an error which is basically the absolute error than a square error, because a square error can kind of blow the error up, particularly when we have outliers. So, the idea is essentially as follows: we want to minimize the maximum degradation. In that sense, it is a min max sort of optimization. We construct a loss function L of d comma y. D is my desired response, y is the estimator output, and I formulate this loss function as mod d minus y, and from this loss function I formulate the epsilon insensitive loss function. What this means is pretty straightforward. If d minus y, the absolute value of d minus y is within an epsilon tolerance, my loss associated is 0, otherwise it is going to be mod d minus y minus epsilon, right. So, this can be seen through this diagram, this function can be visualized here. This is like a bathtub function, right. When d minus y is sandwiched between minus epsilon and plus epsilon, it is 0, else it is mod d minus y minus epsilon, and this is our epsilon insensitive loss function, because it is insensitive in this region. It is insensitive up to an epsilon loss. Okay. I would say up to epsilon parameter instead of loss, up to an epsilon interval, right, minus epsilon to epsilon, and it is the length of the interval is 2 epsilon. So, it is insensitive over this interval from minus epsilon to plus epsilon. Now, with the knowledge of the epsilon insensitive function that we have formulated, we would like to look into the SVM towards the nonlinear regression problem. So, consider the nonlinear regression model. D equals f of x plus v, f is an unknown function, x is a vector, statistics of noise v is unknown, and d is the response that we get. So, we have the training set which is comprised of xi di pairs I equals 1 to n, and our goal would be to get an estimate of the dependence of x, dependence of d on x. Okay. Now, what is the idea here? We would like to estimate d using a linear combination of some nonlinear basis functions. And the idea that we had by incorporating nonlinear functions over points in the input space sort of helps us towards this formulation. Now, y is basically summation j equals 0 to m1 wj times phi j acting on x. This can be thought of as the inner product between w and phi of x, where w is the weight vector w naught so on till w m1. I am folding the bias in the first coordinate, and phi of x is phi naught x so on till phi m1 x with phi naught of x 1, because I have to accommodate the bias. So, this is a pretty straightforward formulation. Now, I would like to minimize the empirical risk given by this quantity 1 upon n summation I equals 1 to n, the loss associated with di and yi, the epsilon loss insensitive function. I invoke this subject to the norm of the weight vector, which is less than or equal to some quantity C naught, right. But I can fuse my constraint to minimize this norm and the risk together. So, what we do is as follows. We would like to formulate this as a constraint optimization problem by introducing two sets of slack variables, zeta I equals 1 to n and zeta I prime I going from 1 to n. So, what we have are the following constraints. So, zeta I and zeta I prime, they have to be non-negative. Those are the two constraints at the bottom, and consistent with my epsilon insensitive loss function, d minus in this region d minus y, which is w transpose phi of x, has to be greater than epsilon, right, or this d minus y minus epsilon is positive. So, I negate it and I get the second constraint. So, similarly the other way around, I have for this part, which is I would say part 2, and this part which is part 1. So, for both of these parts I formulate my constraints and I can represent them using inequalities like this. Okay. Now, once I define my constraints, I formulate my cost functional. The first part of the cost functional corresponds to a quantity where we have to minimize the number of misclassified points, and I think we saw this sort of idea when we discussed nonlinearly separable patterns and design of SVMs for nonlinearly separable patterns, where we had the classes that lie on either side of the optimum hyperplane and they are misclassified, and we formulated an average risk for this and set this up with an optimization problem, right. The same way we do this for this case. The second term is basically the norm square of the weight vector that I need to minimize. So, in some sense I am also bringing this notion of maximizing the margin of separation by trying to minimize the norm of this weight vector. So, I have two constraints that I fuse together as my cost functional, and I want to minimize this cost subject to the constraints that I have in terms of the slack variables and associated Lagrange parameters and other constraints that I had in terms of the first two constraints connecting di, the weight vector w, and then the nonlinear transformation on the vector xi. So, this Lagrangian has several parameters inside the arguments. W is the cost, zeta and zeta prime are the slack variables, and if you want to be savvy you can bring in this notion of vector here, because I can have all the I equals 1 to n variables stacked to form the vector. Similarly, we have the Lagrange multipliers alpha and alpha prime, and also Lagrange multipliers gamma and gamma prime that correspond to the constraints on the slack variables, because the slack variables have to be non-negative. So, I have to bring in the Lagrange multipliers corresponding to that constraint. Now, I have to optimize. So, I have to set up the Lagrangian and then optimize with respect to the various variables that I have in my Lagrangian, and I take the partial derivatives of the Lagrangian with respect to all the variables, set those equal to 0 and then proceed. So, my J is a really messy functional. It has 1, 2, 3, 4, 5, 6 terms. So, you can see these terms directly. So, this part corresponds, the first 2 terms correspond to the cost, right, and the next 2 terms correspond to the conditions, for the first 2 constraints that I have that link the Lagrange multiplier alpha, I mean that link W, phi and D, right, for the 2 regions in my epsilon insensitive loss function, and the bottom 2 constraints are conditions for the slack variables. So, these are conditions for the constraints over the epsilon insensitive loss function. Okay. I do not want to read out the terms. If you can see through it, you can visualize that the last 4 constraints, the last 4 expressions are for the constraints, and the first 2 expressions are towards the cost. Now, we need to optimize this Lagrangian over the parameters, and that is what we need to do. So, setting the derivative of the Lagrangian with respect to the weight vector to 0, I land up with this equation W equals summation I equals 1 to n alpha I minus alpha I prime times phi of xi. This is what I get, and you can straightforwardly verify that gamma I and gamma I prime are linked to alpha I and alpha I prime through this constant C, and that puts the constraint on alpha I and alpha I prime. So, if you cannot verify this, this will be tested on the homework when you do the course. So, one can formulate the dual problem towards maximization like the way we have done. So, in the dual problem we formulate it in terms of the Lagrange multipliers, and I want to maximize this function q over alpha I and alpha I prime. So, this is my dual cost function, which looks like this, right. Here it involves the inner product kernel k acting on xi and xj. So, it is very straightforward from the by computing the partial derivatives of the Lagrangian of the primal problem over the with respect to the parameters, I fuse that and I can into the primal problem and I rearrange to get the dual problem, right. I want to minimize something there and here I want to maximize something here by doing a negative on the cost of the primal. So, this kernel is basically the inner product of two functions phi transpose of xi and phi this is the inner product of two functions phi of xi and phi of xj, right. This is the inner product of phi of xi and phi of xj. Now, you have to bear in mind given this dual problem what is the significance, right. We are given the training data, this is our training set that comprises of points xi and di, I going from 1 to n. We need to figure out these Lagrange multipliers alpha I and alpha I prime I going from 1 to n that maximizes this dual cost and subject to these constraint equations that I have specified. Okay. Now, once I compute the optimum weight vector W, then I can arrive at the regression vector f given by W transpose phi of x, and this takes this compact form summation I equals 1 to n alpha I minus alpha I prime. This is the difference of the Lagrange multipliers over the constraints on the epsilon insensitive loss function times the kernel x comma xi. So, the only thing that is sort of free in this setup, free parameters in this that are free parameters in this setup are epsilon and this constant c, which is used as a scale towards the summation of the slack variables. Okay. So, epsilon and c are not optimized, they are free parameters. So, given that the rest all can be formulated and optimally solved, they can be set up in an optimization framework and solved using an optimization solver to get the right parameters, and then from there we get the optimum hyperplane, and from there the optimum we can get the optimum vector using which we can compute the regression function. Okay. So, there are a lot of details here. I think this particular problem, that is a nonlinear regression problem, was slightly more involved, and that was because we had 4 different constraints, 2 constraints pertaining to the epsilon insensitive loss function and 2 constraints for the slack variables, and we had the cost functional involving 2 terms, one requiring the norm on the weight to be minimized and other to minimize the misclassification error, right, the risk on the misclassification. So, using these costs and associated constraints, we had to solve a slightly messy optimization problem here, but hopefully with this module you can appreciate what goes on in how we set the optimization problem and how we solve these problems in general, and that completes the SVM design, a general framework. Post this we will revisit the XOR problem, and I will discuss that through an example how using SVMs we can solve the XOR problem.